let's learn about the speed of sound in different substances. Our vocabulary: supersonic speed, Mach, sonic boom, pitch, sonic waves, ultrasonic, and infrasonic. Sound can travel through any substance that it can oscillate in order to make waves. Sound travels differently in different substances. So let's take a look at some of these substances. We have air, which is a gas, and it travels at the speed of sound, 346 meters per second. Take a look at steel. Steel, the speed of sound is 5,029 meters per second. Water is 1,435 meters per second. Glass, which is the highest on this chart, is 5,503 meters per second. There's a trend in the data. Air is a gas, alcohol and water are liquids, and other items are solids. The speed of sound in the liquids is 3 times the speed of sound in air. The speed of sound in the solids is somewhere between 2 and 5 times higher than the speed of sound in the liquids. If an object travels in a medium faster than the speed of sound in that medium, then the object is traveling at supersonic speeds. So if it travels in air faster than the speed of sound, it's traveling at supersonic speeds. Supersonic speed is any speed that is faster than the speed of sound in the substance of interest. As an example, the speed of jets is measured in terms of the speed of sound, and this speed unit is known as the Mach number. The speed of a jet traveling in air at the speed of sound is traveling at Mach 1. A jet traveling at twice the speed of sound is moving at Mach 2. An F-35 Lightning II jet, which is a military strike fighter, travels at a maximum speed of Mach 1.8. The NASA Space Shuttle, when landing back on Earth, exceeds speeds of Mach 10. A phenomenon known as a sonic boom is generated when an object travels through air faster than the speed of sound. A sonic boom is basically the sound produced as a result of an object traveling at or above Mach 1. When a jet travels through the air, it produces pressure waves that travel through the air at the speed of sound. So here's this jet traveling, it's producing these waves. As long as it's traveling less than Mach 1, the waves travel in all directions, including ahead of the plane, so they surround the jet. As the jet reaches Mach 1, it begins traveling at the same speed as the pressure waves, and you can see that the wave actually begins here at the nose of the jet. As a result, the waves bunch up in front of the jet. Once the jet exceeds Mach 1, it outruns the pressure waves it's making. The result is a cone-shaped shock wave. Take a look at this picture. They're actually illustrating the cone shape as the jet moves faster than Mach 1. The result of the cone-shaped shock wave is a pileup of the compressions of the waves. This produces a very loud boom. Sonic booms can be destructive to human ears, buildings, and other objects. They can actually shake things off of a desk, as an example. Jets try to travel in areas of little or no population to avoid damage. You shouldn't have sonic booms happening over a city. So let's talk about sound, wavelength, and frequency. Experiment 14.3 in your text demonstrates a difference of pitch by using a soda bottle. By blowing across the top of the bottle, a sound like a horn is made. By adding different amounts of water or liquid to the bottle, the pitch changes. Pitch is an indication of how high or low a sound is, and that's primarily determined by the frequency of the sound wave. Remember that wavelength and frequency have a relationship. They're inversely proportional. So when the wavelength is large, frequency is small, and vice versa. The difference in pitch comes from the difference of the amount of air in the bottle. So the more liquid, the less air. Blowing into the bottle produces waves of air that moved up and down the bottle. An empty bottle produced sound waves with a long wavelength. When the bottle had more water, the waves produced had a short wavelength. Sound waves with a long wavelength have a low pitch, so the empty bottle would have the lowest pitch. Sound waves with a short wavelength have a high pitch. Long wavelengths make low, small frequencies, and small wavelengths make high, large frequencies. Scientists think of sounds as waves in the air, but most of us think of sound as what we hear. And what we hear is actually the signals sent from the cochlea to your brain. The human ear cannot detect all frequencies of waves in the air. Human ears are sensitive to waves with frequencies between 20 Hz and 20,000 Hz. Longitudinal waves with these frequencies are called sonic waves. As an example, the note middle C has a frequency of 264 Hz. Waves with frequencies higher than 20,000 Hz are called ultrasonic waves. Waves below 20 Hz are called infrasonic waves. Some animals can hear sounds that aren't sonic. As an example, bats can hear sounds with frequencies up to 100,000 Hz. A cat can hear sounds up to 40,000 Hz. Whales and elephants can hear infrasonic sounds. So that's it for this unit, and we'll be moving on to 14E for our next video. If you have any questions, be sure to contact me.